Hello, this video is for Stat 110 and includes a discussion of section 5.3, which is going to talk about graphical displays and outliers. Okay, let's go ahead and get started then. So the first type of graphical display that we're going to talk about is what's called a dot plot. The data that we're going to be looking at here has to do with the condition of trees in New York City. So this is data from New York City. It is available on our course website. And here's a view of the spreadsheet for that data. We have the name of the tree, the different areas that it's located in. They actually rated the condition of the tree. They have how big the tree is. And then the last value over here is how much is the tree worth, the value of the tree here. So we're going to be making graphical displays here for the value column. So a dot plot is the first display that we're going to look at. And a dot plot is probably the simplest display. And that is just that every single measurement or row in my spreadsheet is going to have a dot on this display. So here you can see that most of the trees are between about 0 and what is that, $1,500 or so in terms of their value. So I got a lot of trees in this region. And then I have a few trees that go from about $2,000 up to $12,000. And then I do have some outliers up here on the right-hand side. So a dot plot is nice because I get to see every single data value. I can easily get an understanding of where my outliers are at. I can see where data is bunched together. Okay. One issue with dot plots is when I get lots and lots and lots of observations, right? I'm just got too many dots on the screen to really be looking at. So then we go to some of our other types of displays or graphical displays. One of the other types of graphical displays that we use that is pretty common is a box plot. Here's a box plot for the data, for the value data here. Now the box plot is drawn and shows us certain characteristics in the data. Let's start with the middle line in my box plot, which is right here. That is the median of these measures. So that middle line right where my cursor is there is going to be the median value of trees. And we can see that that's a little over 1,000, maybe 1,100 or so. The left side of the box is going to be the Q1 or the 25th percentile, which is essentially the median of the lower half of my data. The right side of the box is going to be the 75th percentile, which would be the median of the upper half of the data. So if this is the 75th percentile and the lower edge of the box is the 25th percentile, I have half of my data inside of the box here. And again, when we were looking at section 5.2, the name of that range there is the interquartile range. So the width of the box is the interquartile range. Now let's talk a little bit about the whiskers. So this is the lower whisker. So that's just the line that goes off the left side. And the upper whisker is going to be the line that goes off the right side. What we do to determine the length of the whiskers is we take the width of the box, which is my interquartile range, we multiply that by 1.5, so we expand it a little bit, and then we add that value to Q3. So where this stops, so let's just do that kind of with mental math here. The left side looks like it's about 1,000. The right side is about maybe 5,500. 5,500 minus 1,000 is going to be 4,500 or so. So the width of the box is about 4,500. We multiply that by 1.5. So that's going to be about 6,000 or 7,000 or so. We take our Q3, which is about 5,500, and add 7,000 or so. And then we get up to that 12,500. Okay. Now we would do that on the lower side as well. We would take the width of the box, multiply by 1.5 and subtract it from Q1. Except in the context of this example, that would take us down way down here below 0 or to have negative values, which doesn't make sense. So we actually stop the lower whisker here at the minimum value. Okay, so the reason the one on the left is shorter here is because we stopped that at the minimum value. We would never extend our whiskers beyond the minimum value or on the other side beyond the maximum value. Okay, the reason we use this 1.5 IQR rule for the whiskers is because these points right here, these points right here are going to be identified as outliers. So there's two ways of identifying outliers. The first is the use of a box plot. So we can see we do have some outliers here. Now, in this particular example, the median is shoved way down to the left side. So that means I got a lot of data between this point here and the lower edge. Half of the data is stuck between here. The upper half of the data is really spread out. Okay, so if I were to make a CDF plot of this data, we would have it would be very steep for a while, and then on the upper half, it would just kind of keep going off to the right. So you can kind of, the right half of the data is a lot more spread out than the left half of the data for this particular set of measures. Here's what that box plot looks like without the dot plot underneath it. Okay, so again, the median is shifted to the left. That means that the data is jammed down here. I got a lot of data jammed down here on that lower side. What do you think the dots on the dots here represent just the outliers? So any point that extends beyond the upper whisker or the lower whisker, there might be situations where I have dots on the lower side as well. Those are going to be considered outliers. Now, this is a mathematical way or a formula-based way of determining where the outliers are at. So it looks like anything at about 12,300 or so, or 12,400 is going to be identified as outliers. If we were looking at the data originally, right, I don't know if I would make the split for outliers right here. I might actually make that split for outliers maybe at 14,000 or something. But again, the box plot is doing that with an equation, not using, like myself here, using an I of what I think is an outlier or not. So we don't have to agree exactly with the outlier rule there. And we actually have another way of determining outliers as well. So there's a couple different ways of doing those. Another thing that we can do with our visual displays is histograms. The idea of a histogram is to just make basically a bar graph for how many dots are within this, what we call this bin. So here I have binned up my data from 0 to 2,500, 2,500 to 5,000, 5,000 to 7,500 all the way up. And I'm just going to count the number of dots in each of those bins, 196, 38, 34, all the way up. And then I just make a bar graph of that. So this here would be a histogram of this data. Again, this is nice if I got just way too many dots to be looking at. You can definitely see the skewness here, right? Data is strongly skewed to the right here. So these values up here are going to be my outliers again. It's kind of hard to see where those outliers are at. I just know that they're in this bin. Right? So a histogram isn't real great in this context here to see where my outliers are at. I mean, I know I have some up here, but those are a lot easier to see. The identification of the outliers is a lot easier to see here on my box plot, right? Because I can see exactly where they're at. So that's histograms. When you're making a histogram in a spreadsheet, you do have to be a little bit careful because it will make the bins kind of odd here. So it is making its bin from 0 to 1,470 and 59 cents, and then from 1,470 and 59 cents up to 2,900. Why not just make it 1,500 and 3,000? So sometimes spreadsheets aren't very smart in determining where it makes those bin choices at. You can specify the bins when you're making your histogram in a spreadsheet. Okay, real quickly then, let's talk about outliers a little bit. We did say that box plots are a legit way of identifying outliers. I just need to see any observations that exceed the upper whisker here. And like I said a moment ago, we can have outliers on the other side too sometimes. So that would be any data values that exceed the lower whisker would be an outlier on the lower side. There is so that's kind of a visual way of identifying those. I mean, it does use a formula, but it's more of a visual depiction of where my outliers are at. We do have a another approach that we can use, which is based on a formula, and that is called z-scores. So what a z-score does is just tries to differentiate how far away I am from my average. So here's my data point minus average. So that's just distance back to the middle. Okay. But then I'm going to divide that by the standard deviation. Okay. Now my standard deviation, recall from last week, is the average distance back to the middle. So what this z-score does is it looks at each data point's distance to the middle versus the average distance to the middle. Our rule is if the distance for a data point back to the average, if that's more than double the standard deviation, okay, so I would have a z-score that's more than 2, or you can have negative z-scores, so less than negative 2, then you're going to be an outlier. Okay, so these are called z-scores, sometimes called standardized values. Let's talk about some of the comments here. Every single data value is going to have a z-score because I get data point minus average divided by standard deviation. So I got to do this for all of my data points in a data set. If my z-score is small, so close to 0, what that means is I'm close to the average. If my z-score is large in a positive way, that means I'm far away from the average and I'm above the average. We'll do some calculations here in a minute and we'll see that. But I could have a z-score that's far away, I could have a data point that's far away from the average on the left side, like below, to the left. So then I would have a negative z-score because the data point would have a value far below the average. Okay, so a negative z-score means I'm an outlier on the left side. A positive z-score means I'm an outlier on the right side. A value that's close to 0 means that I'm right real close to the average. Okay, let's go ahead and do some calculations then. Here I have data on the sunshine percentage for many different cities across the United States. Okay, so let's pick on Flagstaff, Arizona. Throughout the year, you can expect the sun to shine about 78% of the time. Here's another one in Phoenix. These are quite high here. Okay, Yuma, Arizona, the sun shines on 90% of the days, so that's pretty good. But if we go to Little Rock, Arkansas, the sun only shines about 62% of the days. Or Eureka, California, it's even lower at 51. So these are my values here. And I'm going to compute some z-scores for these sunshine rates. I'm going to try to figure out where my outliers are at. So the first thing I need to do is get the average and the standard deviation of my sunshine. Those are going to be 60.28 and likewise for the standard deviation 10.12. Now I got these from a pivot table. Okay, that's where I do my summary statistics with my pivot table. Now if I want to compute a z-score, I'm going to do that for all of my different data values in this spreadsheet. The data value sits in cell C2, it looks like. So I'm just going to take C2 minus my average, which is 60.28. That's my data value minus my average. And then I need to divide that by the standard deviation, which is 10.12. So for this particular location, I get a z-score of negative 0.32. Now what that means is that this location is a little bit below the average. So the average here is 60.28. My data value for this location, which was what, Birmingham, CO, Alabama. Okay. That data value is 0.32 standard deviations below the average. So that's the interpretation of that. These windows that I created for you here are the standard deviations, right? That's the 10.12 would be one standard deviation, or I could go another 10.12, that would be two standard deviations. Here I'm going to the left 10.12, I could do another one to the left if I wanted. So this particular data point, 57, sits 0.32 standard deviations below the mean. So that's not really an outlier, right? That's pretty close to the mean. Okay, these data values here are going to be outliers. And the reason that these are going to be outliers is because they sit more than 2 standard deviations below the mean. Okay, so this is 1 standard deviation. Let me just show you here. If I go out 2 of these boxes, so 10.12 is 1 standard deviation, do another one. So this is going to say anything that's less than about 40 is going to be an outlier on the low side. So these 3 locations right here are unusually cloudy, I guess. The sunshine rates are really low. And those locations, if I go back into my data set, I computed the z-scores and then I actually sorted them, you can see that they are Juneau, Alaska, which is basically -3. So what that means is Juneau, Alaska sits 3 standard deviations below the mean, and that's going to be unusual. Mount Washington, New Hampshire, -2.7. Whatever this town is in Washington, that's -2.7. So I do have 3 outliers here on the left side. This location in West Virginia, Elkins, is right on the edge of being an outlier or not. So that's that 40 that's sitting right there. Now on the high side, it looks like I got 1, 2, 3, 4, 5, 6, is it? Data values on the high side that are outliers. Again, they sit beyond 2 standard deviations above the mean of 60.28. And those are going to be Texas, El Paso, Texas. I got some Arizona, Nevada, California. On the very end extreme is Yuma, Arizona. Yuma, Arizona sits about 2.94 standard deviations above the mean. Okay, so those would be the outliers that I've identified using the z-score approach. We could compare them with what we got against the box plots. And in this particular case, the box plots for sunshine and our z-score approach, they're going to agree. These 3 are identified as outliers on the lower end, and these 6 up here are identified as outliers on the high end. So that's how we identify outliers. We got 2 different ways of doing that, either through the box plots or the more formal z-score approach or standardization approach. Okay, that does it then for section 5.3. Thank you for listening and have a good Thanksgiving.